So let's start. So welcome everyone to the first workshop of Pixelate this year. So if you've actually taken part or heard of Pixelate in the last year, what Pixelate is, it basically is an event where a bot navigates a kind of a maze. So the way it navigates the maze is up to you. So it should navigate autonomously. So there should be no manual intervention from the bot. And this is last year's PS. So if I just give an example, what starts from it has to reach here. So it has to go on one of these paths. It has to choose the best path for itself and go to this place. So the best path, as in this, the red square is one where you should try not to go. The white square is one where you should try as hard as possible to go, and the green squares are of varying weights. So these figures are of varying weights. So the bot actually starts here and reaches this point. So that is the aim of the event. So now for this to get this event started, we first start with how to what is the algorithm required to actually go here. So for that, we will in this workshop we will cover Dijkstra's algorithm, and another part of this workshop will be about how you will detect where the bot is. So in an offline event, you can actually see the bot and find out where it is. But in an online event, you in the same way you will have a marker on top of the bot. It's called an Aruco marker. So that will be explained as well. So I'll hand it over to Lakshit, who will start off with the Dijkstra's implementation. Lakshit, over to you.
Yeah, hello. Thank you, Vaya. Hello, everyone. I'm Lakshit from Electrical Part 2, and I'm member of Robotics Club. And so today I'll be explaining you about the Dijkstra's algorithm. So my screen is visible.
Yeah, it's a little.
Okay. So this algorithm is mainly used for solving robot path planning problems, as you have seen in the previous arena shown by Vikyat Bhaiya. So it is one of the most popular algorithms used for solving the shortest path problems. It is used to find the shortest distance between two vertices on a graph. And apart from this application, it is also has many real-world use cases, including digital mapping services in the Google Maps. And so let's learn what is graph. Graphs are data structures which are used to represent the connection between pair of elements. So as you can see in this image, these circles represent nodes. These nodes are the elements which graph will represent. And in last year's arena, those square tiles were the nodes. And these edges represent the path which connect these nodes. And these numbers on the edges represent the weight of edge. You can consider it as for example, let this 5 is the distance between as node 1 and node 0. So these are nodes and edges. So we have understood this by looking at the image, but how will our computer understand? For that we have adjacency matrix. This matrix represents just simply we can say it represents the edges and the weight of the edges, and also represent that if any two of the nodes are connected or not. If there are n nodes in the adjacency matrix, sorry, if there are n nodes in the arena, then there will be n rows and n columns in the matrix. So as you can see here, so how can we, what are the values which define this matrix? So this diagonal in this matrix, all the diagonal elements are 0, because for example, let's say any node, the index for this node is 0, 0. So it will represent the distance required to move from that 0 node to 0 node. So it will be obviously 0. And let us take any random index, for example, this 15. My cursor is visible, right? Anyone?
Yes, yes.
Okay. So for this node, the index is 1 comma 2, and this value 15 represent the edge of weight of that edge which connect the nodes 1 and 2. So this is confirmed from this image also. And one more thing you can confirm is that this matrix is symmetrical about this main diagonal. So all these values about this main diagonal are equal, like 1 comma 0 and 0 comma 1. This, and the reason is simple, that the weight of this edge does not depend on the direction in which we are going. For example, we go from node 0 to node 1 either, or we go from 1 to 0. This weight will be same, but this is not the case every time. The weights might depend on the direction of path. So let's see with an example. In this image, you can see there the path connecting node 3 and node 2 have different weights depending on the direction. If you go from node 2 to node 3, the weight is 3, and if we go from node 3 to node 2, the weight is 2. And this is visible in this matrix also. At index 3 comma 2, it is 2, and 2 comma 3, it is 3. Okay. So now I will be explaining the actual steps of this algorithm with a simple example of this graph. So first of all, let me explain what is distance value for a particular node. It is just the, we can say it is a value which represents the total distance which is required to travel from the starting node. For example, let's say we travel from node 1 to node 0 to node 3. So the distance value will be 5 plus 2, that is 7. And so the initial setup for Dijkstra's algorithm will be that we assign a distance value of infinity to all the nodes except the starting node. And here the problem is to go from node 0 to node 6 using the shortest path possible. So this is the initial setup. The distance value is 0 for starting node, and all elsewhere it is infinity. So now the first step for this algorithm is to consider all the unvisited neighbors of this current node 0. We have to consider unvisited neighbors in node 0 and node 2, and we have to update their distance value only if the new distance value is less than the current distance value. So if we try to update distance value of node 1, so it will be 2, which is less than infinity. So it will be updated. Similarly, node 2 will be updated, as you can see. So the next step number 2 is after considering all the unvisited neighbors, then we have to mark the current node as as visited node. So I have represented a current node as red color circle. Now, as we mark it as visited, we mean that we will not consider it again. So I represented as green circle for a visited node. Now the next step is to select a new current node, and for that we have to consider all the unvisited nodes, like this is 1, 2, 3, 4, all except this visited, and we have to choose the one which has least distance value. So this node 1 has least distance value, it will be the current node. And then again we have to repeat the 3 steps which I told earlier. First was to consider all the neighbors, unvisited neighbors of this current node, and try to update its distance value. So for unvisited neighbor for this node is only 3. So distance value will be 5 plus 2, which is obviously less than infinity. So it will be updated. Now, second step, again, mark this as mark the current node as mark the current node as visited node, and again choose a new current node. So this time it will be node 2, as you can see in this image. Now again we have to repeat these steps until we get to this goal, that is node 6, and this node 6 is marked as visited. We have to repeat the steps. So let's first try to first step, again we try to update the distance value of unvisited neighbors, that is node 3 again. If we try to update, then it will be 8 plus 6, that is 14, but it is more than 7, so it will not be updated. So we will directly mark node 2 as visited and node 3 as current node. Now again, step 1, we will update. These values are infinity, so they will get updated. And now step 2, it will be marked as visited, and out of 22, 17 and infinity, 17 is the least. So node 4 is current node. Then again the same steps. Node 6 will be 17 plus 2, 19 distance value, and for node 5, if we try 17 plus 6, 23, which is more than 22. So it will not be updated. And in this way, again, this node is visited, and out of 5 and 6, 6 will be the current node. Now, as you can see, we have reached the goal, but still one step is left. So let's complete it. Try to update the distance value of this node 5, which is the unvisited neighbor for this current node. So again, 19 plus 6, 25, but it is more than 22. So we will not update it, and this will be marked as visited node. So this, you have got the path. These were the steps for Dijkstra's algorithm. Thank you. Now let us do very quick exercise before Soumya takes over. Anyone of you remembers the steps which I told? If yes, then you can speak, else we can go further.
किसी किसी को नहीं समझ आया क्या, या लाइक एटलीस्ट एक बेसिक आइडिया ट्राई भी कर सकते हो, कोई दिक्कत नहीं, बट एटलीस्ट अ गुड आइडिया व्हाट एग्जैक्टली स्टेप्स थे किसी को है?
क्या भैया? आई एम
ठीक है, नेक्स्ट. Yeah, you can go ahead and explain like all these steps in brief.
भैया, are you asking me to explain?
Yeah, just repeat those steps if you remember.
Just a brief overview will be fine. You don't have to repeat each step. Just a small overview.
Hello everyone, I am Shrutija. I am from first engineering student. Now I remember. I don't remember trying to do that. The thing. Hello.
I think your voice is breaking. Your net. I don't think your network is strong enough.
Am I audible now?
Yeah, it's better now. Yeah.
So he just can I speak explain in Hindi?
Sure, sure, yeah.
हाँ तो उन्होंने पहले बोला वो जो नोट्स होते हैं हमें सबसे पहले कवर करने की शॉर्टेस्ट पॉसिबल पाथ से हम लोग को अपने गोल तक पहुंचना होता है तो हम लोग एक नोट फर्स्ट हमारा जो स्टार्टिंग पॉइंट था वहां से हम लोग गए फिर हम लोग उसका देखेंगे कि वो कौन कौन से डायरेक्शन मतलब और टोटल पॉसिबल नोट्स कौन कौन से हैं तो उधर जाते हैं पहले वैल्यू असाइन उस वैल्यू से हम कर सकते हैं तो हम लोग ट्रैवल करके जा सकते हैं ऐसे करके फिर देखना होता है पाथ जा सकते हैं एंड अगर उस असाइंड वैल्यू आती है तो फिर हम लोग फिर जाते हैं एंड था करंट नोड होता है ऐसे करके करंट जगह पे अनविजिटेड एंड वहाँ पाथ का यूज
Okay, your voice is breaking, then we will move further. Soumya.
Yeah. Okay. So thanks, Lakshit, uh, for your presentation. So Lakshit basically explained like what the algorithm basically does, how the algorithm actually works. So let's now jump into the implementation of the algorithm. Is my screen visible? Hello.
Yeah, it's visible. Yeah.
Yes.
Okay, so let's just see how to implement Dijkstra in matrix format. So here the arena which you will be dealing with. It constitutes of some tiles and each tile has some color and that color determines the weight of that tile. So how much effort you have to put while reaching that tile. Okay, so here I have taken 4 tiles for example. So black tile, it has a weight of infinity, means it's a kind of prohibited region, so you cannot go there, and if you go there then infinite weight will be charged. Okay, and green tile has a weight of 3, red has a weight of 2 and purple has a weight of 1. So like from any tile, if you move to the purple one, then one weight will be charged, or you can say that an effort of 1 unit it has to be applied. While from going from any tile to the red tile, it will cost a weight of 2, and for green tile it will cost a weight of 3. Okay, so using some OpenCV techniques, you have to determine like what all are the colors of your tiles, and then you can just arrange them in a matrix format as shown here. And here I've marked the starting and ending points. So the purple tile is the starting point and this red tile over here, it's the ending point. So we have to find the shortest path to reach this end point. Okay. So like firstly the indexing is done of various tiles. So we can just start from here. It's the first tile 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. So this is how we can index these tiles. Yeah. So next, these are the weights of the tiles written. So as you can see, all the green tiles, they have a weight of 3, red tiles have a weight of 2, and purple tiles have a weight of 1. And all the black tiles, they have a weight of infinity, which means that they are the prohibited regions. So now let's just implement the algorithm. So for each tile, we have a value of D, V and P. D is the distance for that tile. So as Lakshit explained, like distance means what is the total distance you need to travel to reach that tile from the starting tile or the starting position. So what is the total distance that you have to travel to reach that tile from the starting tile? So distance you can consider like more the weight, more is the distance. Okay. Next is V. V is the visited value. So V equal to 0 tells us that the tile has not been visited, and V equal to 1 means that tile is visited. Next P. P is the parent of that tile. So like suppose I have this purple tile over here, and suppose I reach this tile from this tile. Okay. So this purple tile, it has an index of 3. So the parent value of the second purple tile, it will be 6 because it's the child of the, it will be 3, sorry, it will be 3 because it's the child of this third tile. Because to reach this purple tile, you reach this purple tile from this third tile. So the parent of this purple tile is at index equal to 3. So the value of P will be 3 for this particular tile. Okay. And one more thing to note, that suppose you visit a tile, okay, and once you have figured out now that what all are the neighboring tiles of that particular tile, only then you mark it as visited. Start the implementation. So this is the beginning tile. Initially the value of V will be 0 for this tile and for all the other tiles. Okay, and the value of P will also P will be infinity for all the tiles, because since we have not reached all of these tiles, so obviously there is no parent for them. So infinity is what we have already assigned the parent value for all of them. Okay, now for the first tile, D equal to 0. Because to reach the starting point, from the starting point you don't need to travel any distance. So initially D equal to 0 and its parent we have marked as 0, just to show that yeah, we have reached this tile. Now next we have to figure out that what all are its neighboring tiles. So from this tile, either you can move up, right, or to this diagonal direction, but this upward tile is prohibited. So this green tile and purple tile, these are the neighbors of this original starting point. Okay, and to reach this purple tile, since this purple tile has a weight of 1, so the value of D will be 1 for this tile, and the weight of green tile is 3. So to reach this green tile from this purple tile, you need to travel at a distance of 3. So the value of D for this green tile will be 3. And both of these tiles, they have a parent at index equal to 3. So their parent value is updated as 3. Okay, so now you can see that this purple tile, we have found the neighbors of this purple tile. So this tile should be marked as visited, right? So in the next slide, you can see that now this purple tile is marked visited. And now these both are the unvisited child tiles, you can say. Okay, now out of these two tiles, this purple tile has the minimum value of D. So now this should be a current node or current tile. And now we should start figuring out what all are the neighboring tiles of this current purple tile. So from this current purple tile, either you can go upwards, okay, you can go at this diagonal direction to this black tile, but it's prohibited. You could have gone to the left, but this purple tile is visited already, so we ain't going there. So what all are the remaining options? Either go to right, green tile, or go to this diagonal red tile, or go to this upward green tile, because these are the unvisited tiles. Okay, but we cannot go upward. Why? Because the D value of this upward tile is 3. But if you go to that tile from this purple tile, then a total distance of 4 will be there. Why? Because 1 you have already traveled. Okay, and this green tile has a weight of 3. So 1 plus 3, that is a total of 4 distance you have to travel to reach this green tile from this below purple tile. Okay, so total D will be 4 for this green tile, while already the value of D is 3. So we won't update it because we want the value of D to be minimum. So let's just forget this child. So next we have these two red and green neighbors. So these are the new neighbors of this purple tile, and hence see, so the value of this, the index value of this purple tile is 6. So the parent of this red and green tile is 6. And the distance value, you can see it's updated. See, the value of red tile is 2, the weight of red tile is 2, and already we have traveled a distance of 1 at this purple tile. So 1 plus 3, 1 plus 2, that is a total distance of 3 that we have to travel to reach this red tile. And the weight of green tile is 3. Weight of green tile is 3, and already we have traveled a distance of 1. So 1 plus 3 equal to 4. That is a distance of 4 we have to travel to reach this green tile. Okay, now we have figured out what all are the neighbors of this purple tile at index 6. So let's mark it as 1. Let's mark it visited. Okay, now we have these 3 unvisited tiles. This green tile, this red tile, and this another green tile. Out of these 3 tiles, the value of D is minimum for this upper green tile and this red tile. So we can just choose any one of them randomly. Yeah, so let's just choose this green tile. Let's just choose this green tile. We have to find out what all are the neighbors of this green tile which are unvisited and where we can reach. So this black region we cannot reach. These purple tiles are unvisited. Okay, so this red tile over here, it is the neighbor of this green tile. Okay, and red tile has a weight of 2 and this green tile has a value of D equal to 3. Right, so to reach this red tile, 3 plus 2, that is a total of 5 distance we have to travel to reach this red tile. Okay, similarly this red tile over here, it is also the neighbor of green tile. So this D is 3. 3 plus 2, 5 distance we have to travel to reach this red tile, but already the distance is 3. So we need to minimize this distance. So we won't consider going to this red tile. Similarly, this green tile over here, it's also a neighbor of our current green tile, but to reach this green tile from this current tile, we have to travel a distance of 6 because already D equal to 3 and this green tile has a weight of 3. So 3 plus 3 equal to 6. So a total of D equal to 6 we have to spend to reach this green tile from this parent green tile. But already there is a distance of 4 and we want to minimize D. So we won't reach here from this green tile. Okay. So now you can see that the new neighbors that we have found out are this red tile which has a parent of 5 because the index of this green child is 5. Okay, now we have found out what all are the neighbors of this green child. Let's mark it as 1. Now the unvisited tiles are this red tile, and this green tile. Now let's look at the values of D. We can see that this red tile over here has the minimum value of D. So let's mark it as the current node. Now find out what are the neighbors of this red tile, unvisited neighbors. So obviously this black region, it's prohibited. These both tiles are visited. This green tile over here, it's a neighbor. This black tile is prohibited. This purple tile is a neighbor and this red tile over here, it's a neighbor. So yeah, let's just update the values. Already D equal to 3, weight of red is 2, so 3 plus 2 equal to 5. A total of D equal to 5 we have to travel to reach this red tile. Similarly, the weight of purple is 1 and we have already traveled D equal to 3 at this red tile. So 3 plus 1, that is 4 distance we have to travel to reach this purple tile. So as you can see, the parent value of these both of these tiles is 8 because the index value of this particular tile, red tile, is 8. We haven't updated the D value for this green neighbor node. Why? Because to reach this green node, see the weight of this green node is 3 and to reach this node from this red node, 3 plus 3, that is D equal to 6 we have to spend, but already we have a value of 4 for this D, so we won't update it. Okay, so now we have found out what all are the neighbors for this red child, red node, red tile. So let's just mark it as 1. Now the unvisited nodes are this green, this purple, this red, and this red over here. And out of all them, the minimum value of D is for the minimum value of D is 4 and it's for this purple tile and green tile. So we can choose any one of them. So let's just choose this green tile. Now as you can see that its neighboring tiles are these 3 tiles. First, these are visited. This black tile we cannot go because it's prohibited. So its only neighboring tile is this purple tile over here. But purple tile has a weight of 1 and current node has d equal to 4. So to reach this purple tile, the total distance we have to travel is 4 plus 1, that is 5, but already d is 4, so we won't update it. So yeah, we have traversed all of the neighbors of this current node. Let's just mark it as 1. Now the remaining unvisited tiles are this purple tile, red tile and this red tile. Out of all them, the minimum value of d is for this purple tile. So let's just find out what all are its neighbors. So you can see that this black tile it's a neighbor, this black tile it's a neighbor, but they are prohibited. Both of these are visited nodes, so this is an unvisited neighbor for the purple tile, and also these 3 tiles, these are the unvisited neighbors for this current purple tile. So let's just mark the neighboring tiles. So d equal to 7, d equal to 6 and d equal to 6, and all of their parents are 11 because this purple node it's at 11th index. Now these are unvisited nodes, and we haven't updated this upper red tile. Why? Because again the weight of red tile is 2 and we have to travel 4 plus 2, that is 6 distance to travel to reach this red tile, but currently d is 5, so we won't update it. Now we have found out what all are the neighbors of this purple tile, so let's just mark it as 1. Now we have unvisited nodes. See this red tile it's unvisited, and all of these tiles are unvisited. So out of all these tiles, the minimum value of d is 5. So d equal to 5 for this tile and d equal to 5 for this tile. So let's just randomly select this tile as my current node. Now you can see that either its neighbor is visited or prohibited. So all of its neighbors are traced, and let's just mark it as visited. So yeah, now next tile which has the least value of d is this red tile. Now it's turn to find the neighbors of this red tile, and after finding its neighbors we will mark it as visited. And what is our main purpose? To reach to or to visit this red tile, because this was our goal, this was our ending tile. So we don't need to find its neighbors, let's just mark it as visited, because our ultimate goal is to just visit this tile. So yeah, this tile is visited, and as you can see that every time we visit a tile, every time we reach a tile we mark its parent tile, right? So the parent tile for this red tile is 8, so this is the 8th tile. Yeah, now for this tile the parent is 6, so let's just use backtracking. The parent tile for this particular tile is 3, so let's just move to the tile 3. So as you can see, we have backtraced the path, and hence we have found out what is our final path. Thank you. So next, Asit will tell about Aruco markers.
Asit, you're muted.
Yeah, sorry. Yeah, so good evening, everyone. Thank you, Soumya. I'll be introducing you to Aruco markers. So I'll just share my screen, and hopefully the screen is visible. Can anyone just confirm?
Yeah, it is visible.
Yeah, okay, thank you. So Aruco markers. So just pay a bit close attention to this thing present right here. Hope my cursor is visible too. Okay. So what are Aruco markers? Aruco markers are basically 2D binary patterns. So obviously a 2-dimensional binary pattern because it's a simple black and white, and it can be detected easily by simple computer vision algorithms. And why do we use it? So it can uniquely identify the body it has been pasted upon or attached to, and along with doing some computation on the data we get, I'll be explaining that, we can get the position and its orientation also. And obviously it looks something like a QR code, but trust me, you won't get anything after scanning it. So it's just think of robotics. Now, in short, I'll just explain. This is the basic structure of an Aruco marker. So first of all, you'll just come to this black border. So this black border is actually called padding. So it's just to differentiate the Aruco marker from the rest of the image, like rest of the thing, to like, remove the noise or remove the chances of getting misread. Okay, so this is just a simple border. And the main thing that uniquely identifies in a marker is this grid. So this is a 5 cross 5 grid. It's visible. Okay, and the grid, the size of this grid can vary from 4 cross 4 to 7 cross 7 for Aruco markers, right? And for uniquely identifying each grid, like each Aruco marker, we have some sort of encodings in here. So if you consider these columns, so these are distributed in columns. If you look at the odd columns, these are defined as parity bits, and the even columns are derived defined as data bits. So what are data bits and parity bits? So data bits are actually the bits which actually like together contain the main ID of the Aruco. The parity bits are just for cross verification. So we some sort of like real world environments, it can be some problems. So just for cross verification, the parity bits are there. All the markers can the ID can be exactly extracted just only from the data bits. Okay, so in this example, you can clearly see that there are 5 rows and there are 2 columns for data bits. So total 10 data bits are there. And obviously each is a binary number. So the possible number of combination for data bits is like 2 to the power 10, 1024. Okay. Now we'll just explain how we actually are going to use in our Arduino projects, because there's no use of theory without implementation. So obviously M1CV, the best library, it has a module for Aruco, and the related functions are quite easy to operate, and we'll be just explaining how to do that. So first of all, we need Aruco markers. So we will just generate Aruco markers in the first script, and as simple as that, we'll first of all import the necessary libraries. So NumPy, and this is CV2, the OpenCV library, and we'll just separately import Aruco module as Aruco, because just we don't want to write a cv2.aruco every time we need to. It will just make a code easier. Okay, so just imported the libraries first. The next thing we want to do is Aruco model has some predefined collection of predefined collection of these Arucos. These Arucos of one pattern. So there are multiple patterns of this thing, and there are some predefined dictionaries in here which will have like multiple collections of this. So in here, if you see, I have used a keyword called dict 5 cross 5 250. So 5 cross 5 explains the grid size of that unique ID one. Okay, so I just tell you that it can vary from 4 cross 4 to 7 cross 7 and stuff. So this is for specifically for 5 cross 5, and the 250 number indicates the number of unique Arucos present in that dictionary. Okay, so this is a keyword, and this is the function. We pass this attribute in this it's sort of an unique integer ID, and we get the dictionary. So this dictionary will now be having 250 different unique Arucos of size 5 cross 5, right? And some other dictionaries are available too, like this one. So there are 4 cross 4, 6 cross 6, and the number of samples in each dictionary can vary too. So we try to keep it minimum to conserve more memory, obviously. And Aruco Dict, I just explained you that this is the dictionary with 255 cross 5 markers we just took out. And obviously from 250 unique Arucos, the IDs will be ranging from 0 to 249. Now to make a marker actually, so we have a function called Aruco.draw marker. So draw marker, it primarily takes three arguments. So Aruco dictionary is that dictionary that we just generated, a sample dictionary. Okay, then this is the unique ID of that Aruco specifically. Okay, so this number can vary from 0 to 249 easily, and you will get like different unique Arucos for that. In this case I have taken it 15 to be the today's date. And the next thing is just the size of the image. So this is the resolution of the image, 400 by 400. Obviously Arucos are always square, so this will be a 400 cross 400 in pixels, the resolution of the image marker. And I'll just briefly show you the implementation of this thing.
Asitva, there's one doubt.
Sorry?
Yeah, there's one doubt. Shruti is asking.
Yeah.
You can unmute
Hello,
yourself.
Bhaiya. I wanted to ask, can you just turn to that slide where you just first showed the grid?
This one? Yeah.
You showed like like if we assign that integer value, how do we assign? Do we select it randomly or?
So these, the indexing for the parities and data. What are exactly talking about? I couldn't get you. Maybe.
Please.
Yeah, so there seems to be some network issue. Can you just type in it in the chat box?
Just type it in the chat box and we'll take questions towards the end. Yeah.
Okay,
So you can
sure.
continue.
Yeah, sure. So we'll move on. So for the implementation part, I'll just quickly show you. So this is where I imported all the required libraries, the OpenCV, the Aruco separately, and NumPy. Okay. So first of all, as I told you, we get the dictionary, we get the simple dictionary. Okay. Then we apply that function to draw that image, as I just explained earlier. And this is just a simple OpenCV function to display the image. So I'll just quickly run that. So you can see that this Aruco, this is an Aruco. The unique ID of this Aruco will be 15 as passed, and the like the size of this Aruco image will be 400 cross 400. So if I show you, like if I change it to something like 300, and just rerun it, so you'll see that it goes smaller. So now the size is like 300 pixels by 300 pixels. So that's how that thing works. And if I change this unique ID also, like if I do it something like 55 or something like that, Aruco, the pattern of the Aruco mark also change. So this is the Aruco with its ID 55. Okay. Hopefully this is clear by now. We'll just get it back to 15. And now what we can do is we can just simply save this image. Okay. So when we can simply save this image, the very same image we generated, to like take future references. So when we like, I'll just run the code. Okay, now you can see that this image like now got saved. So you can just get it printed or something like that and just directly paste upon your the objects in real life to be tracked and something like that, so you can use it. Now we'll just move on with the like we have now generated an Aruco marker, and now we'll move towards its detection. Yeah, so for detection of Aruco markers, the required libraries remain the same, all the NumPy and the OpenCV and the Aruco model. And for this, we first of all store the image we want to like test upon. We want to detect samples in an image variable. This is some OpenCV thing. So we'll just use the OpenCV function imread to just read the image and store it in a variable. Okay. Then we preferably convert the image from RGB to grayscale. So actually this helps in more detection of Aruco more efficiently. RGB has 3 channels and like gray is only single channel. So this is just better to be detected. And obviously we'll use the convert color function. I hope you might be familiar with that with the previous workshops. So convert color, and with just proper attribute BGR together, we can get the gray image of it. And after this, we again just select one of the predefined dictionaries. So in which we feel like the RR code like which we want to detect is most likely to be present in. So for a previous example, we created the Aruco marker from this dictionary. Okay, so I know that my dictionary, the Aruco marker I want to detect is going to be from this dictionary also. So I'll just keep get this dictionary and just store it like normal, as done in the previous example. Okay, now this is actually just a parameters function which the detection function needs. So for now, we'll just leave it to like it can actually help us customize the process we want to detect the barcodes in. For this case, we'll just keep the store the default parameter it returns. So we don't need to manipulate right now with that. We just need the function. So we'll just store it in the Aruco parameters. Okay, so the function is aruco.detect parameters create, and we just save it in another variable called aruco parameters. Now, after all this, we try to detect the markers present in the past grayscale image and are accounting for the parameters in the previous step. So parameters are default, so no worries about that. And this is the function for detecting markers. So Aruco to detect markers. Okay, so this is a function, and it's the arguments it takes are as follows. So gray, Aruco dictionary, parameters of this. So gray is the grayscale image we just converted from BGR to gray right now, and the Aruco dictionary. So what we felt our Aruco is mostly likely to win, just created this one. Now the next thing, the Aruco parameters one. So I just told you just in this one, for now we'll just have the default parameters of it, and we'll just pass it to the detect markers function. So it'll detect all markers present in that image, and it will give us three separate variables. So we'll just store them in three separate variables. So first of all, it will return the corners. So what are the corners? Aruco, obviously you can see that Aruco is a square. So it has four corners. So this will be returning the four corners of that Aruco. The IDs, the unique ID of the Aruco is found, and the rejected image points. So this is where the point where I said the data bits and parity bits part come in. So like if data if cases like data bits say some ID and the parity bits say some another ID, so there's a conflict. So the detected marker is not exactly an Aruco 2. So this it got rejected. So this is separately returned. We really don't need to operate with that, but as an since we need to collect three separate variables from this function, we have to keep this. We can just replace it with an underscore or something like that. It's not much used, but we'll just need to we'll need just this thing to be here. Okay. So on a briefly examining the IDs and corners. So corners are actually just an array of 2D positions. So each corner will have some sort of like XY coordinate. And hopefully you know that the OpenCV images, they start from the left upper corners to form the indexing. So there will the four coordinates will be returned XY for each one. So I'll just, like for example, if we use this one, so it xy of this, xy of this, xy of this, xy of this, something like that. Okay. On the order is like clockwise. So it will first try to return the top left one, then it will return the right top, and then it will be returning the bottom right one, and then it will return the left bottom one. So this is, and obviously if there are multiple Arucos detected, the order of like IDs getting through that and corners detecting getting through that will be same. Okay, so I'll just show you a quick implementation of this also. Forget about this for now. Okay, so what we are doing, just we are defining a dictionary. This, as I told, Aruco is most likely to win. We generating the Aruco parameters needed, and here we are reading the sample image to be detected. So here the sample image is this one. Okay, so this is an Aruco marker, and just a normal sample image. Okay, this is the Aruco marker, and if you like pay close attention to it, so this is the same as the one we generated in the first step. So it had an ID with it had an ID 15. Okay, so this one. So when we are detecting this, when we are going to be detecting this Aruco, it should be returning the ID 15 also. So I'll just run it and show you. And obviously then, yeah, so there is a conversion to grayscale, and then the direct markers function, as I just told you. You can just ignore this for now also. I'll just run the function. Okay. So now you can see that. So first of all, it return corners. So corners are XY coordinates of each of the corners of the Aruco. So if I okay, yeah. So the order in this it will be returned is like this corner, this corner, this corner, and this corner. In this very specific image, first of all, this 683,325, this will be the top left corner of this point. Then the next 803,324, this will be the right one, top right one. And you can see that they have approximately the same y coordinate, right? And has the lesser x coordinate. So it defines that this is this point only, and then we go along like that. So starting from the top left in the clockwise order, right? And the ID detected for the
Yeah.
markers is 15. Yeah.
अगर हम लोग को कोई जैसे पर्टिकुलर पैटर्न चाहिए तो हम लोग को उसकी आईडी कैसे पता चलेगी?
See, you can generate it like getting a particular pattern is really difficult. You can look for some resources. Like, what are you exactly trying to say? Like, do you want a specific Aruco like pattern to be generated or to be detected?
To be generated.
Yeah, so that is actually trial and error. So we can't do anything about that. So there are some encoding algorithms for this, like the how the actual and this is like all the grids are encoded. So you can have a look at that how it's actually encoded on net. You may find some resources for that, and you can maybe then get the desired pattern, like reverse calculating it. So this is possible, but it's like not usually done and not preferred.
Okay.
Right. Okay, then yeah, so back to topic. Just as I just told that this sample Aruco that we generated in the first time, it had ID 15. This is the same Aruco, and when we detected the Aruco in the picture, it gave us ID 15. So it's still wrong. Okay. Now for a bit of like more debugging purposes. Okay, then there is a like more like it's not really needed to be like in directly working, but for debugging purposes this function is really good. So it's called draw detected markers. What will it do is it will take the image, it will take the corners of the Aruco and just have a simple border color. So the corners of the Aruco are the same list that we got from this function, this corners already. So you can just directly pass it in here and the image to drop on it and the border color. So if that is visible, that in this case this is the red color. So if this red color is given to it using this function only. So you can just border color equals to give it in BGR values and it will highlight the Aruco with that specific color, right? You can go through the slides if you want detailed documentation. This is wait, and for the implementation part, just quickly show you that. So if I just uncomment this line and okay. So you can see that this Aruco is now highlighted in here. So hopefully this is all like the red lines are visible and this small green square. So this small green square, I hope it's visible. This marks the first point of the Aruco. So as I've been telling you that the top left corner is the like first point to be passed. So this highlights the first point and we can go clockwise from here to get the rest of the points. Okay. Now, what if the markers are like rotated? So I'll just be solving issues with that. So instead of now loading this on the image, now I'll be loading this image. So it's the same exact same Aruco marker. Both are the exact same, but this one is just turned to right by 90 degrees. Okay. So we'll just use on that. Yeah. So hopefully it's visible. So can you see the green squares in there? Someone will confirm it, so it will be good because it's quite small. Anyone?
Yes, we can.
Yeah,
Yes,
it's
Yes.
visible. It's visible.
Okay.
अब यार
So
जैसे
okay.
रोटेट कर दिया है तो अब इसकी दूसरी आईडी हो जाएगी कि वही रहेगी?
No. I'll just brief you upon that. So the markers, the ID will remain the same. Cause so it's pretty much the same pattern. Okay, it's like it's the Arucos are encoded in a way that on rotating one, it doesn't overlap with another Aruco with like it having all of the Arucos have same unique IDs and like unique position and any orientation. So if they are like this way to rotate at 90 degrees to right or left or upside down, so they're made in a way so that they do not
Okay, bhai.
overlap with each other. Okay. So yeah, so what I'm trying to tell you here is that see, this is the upright one, the normal simple one. So it's detecting the corners to be at the top left the first corner to be at top left, and other we can just clockwise order. So it returns in the clockwise order. Okay. Now when we return this rotated this Aruco marker towards the right, so the point, the location of the first point with respect to ID is fixed. Like in the inner grid, if you say it rotated, this part also came to the right. Okay, so the relative location of these will be always fixed. So now this is the first point that will be returned by the function. I'll just quickly show you that we can. Yeah, so you can see that in this one, in the first one. So see, this one is the first one. This Aruco has been detected earlier than that one. So it is having a coordinate of 900 to 222 one. So at the local at the later part, this thing, and then we move clockwise. So x coordinate staying the same, y coordinate increasing. Remember the origin is on this side, this point. So y coordinate increasing. So you can see that this is the next part of this is the right bottom one. So it's moving it's as always like moving clockwise where it's returning the other points. Okay, same with the first one. And since both the Arucos are same, you can see that the IDs they have returned is 15, 15 both. Cool. Yeah, so everyone, any doubts still yet? Okay, I'll assume no. So yeah, what I'll do now is just save this rotated image using the simple IamWrite functions. And you can see that the Aruco detected this is the same image. Like after detecting the Arucos, the image has been saved. Now I'll just quickly brief you how to like get useful information out of these things. So what we have right now, so we have like first of all, this is the first corner, this is the second corner, this is the third corner, and this is the fourth corner. Okay, and we have the xy coordinates of all of these in this very specific order. Okay, now to get the position of this Aruco marker, so what we obviously we can't define it by 4 different points now, so we need a single point. So what we do, we just get the centroid of this Aruco figure. So we have the coordinates of 1, 2, 3, 4. You all know, might be aware of like how to get centroids. Just sum up all and divide by 4. Okay, so this will give you the centroid of the centroid of this Aruco marker, and this will be like the position of the object which we want to detect, right? Cool. हाँ ना, कुछ तो बोल दे यार, बच्चे भी हैं लोग. Okay, never mind, we'll just move on. So now with the orientation part, so just let's assume that the bot is facing in this direction for now. Okay, this is the face of the bot. Now we want to get the orientation of the bot with just 4 corners. So what we can do is either we can make a vector pointing from 3 to 2, or we can make a vector pointing from 4 to 1. Both will represent the same direction, and that direction will be the face of the bot. Okay, so making vectors fairly simple. You just subtract the coordinate of 4th from the first one, just basic maths. Okay, so this will give you the direction in xy like points, and you can actually get the direction of the board using this like this. And for this case, this is this green square part, this will be the first, this will be second, this will be third, and this will be fourth, right? And obviously if the board has rotated 90 degrees, so obviously the Aruco is rigidly attached to the body you want to detect. So only if the board rotates by or the body rotates by 90 degrees, the Aruco will rotate it by. So we now have the face towards this, and using the same concept, any vector from either from 3 to 2, or any vector from 4 to 1. So we can just get the vector by subtraction of the coordinates, and we'll get the orientation of the bot. Okay, so this is the basically like everything you will need to know for solving the arena in the problem statement. So practice upon it, and do ask if you have any doubts.
So that's the end of the session for now. So we'll take doubts now. So thank you all for attending.